Namaskar friends, my name is Deep Pandey and I welcome all of you to Study Way Technologies, and in our today's session we will discuss about time domain representation of LTI system. This is part of signals and system and it is our lecture number 4. So in this session we will focus on the system description that relates the output signal to the input signal when both signals are represented as function of time. So these descriptions are useful for analyzing and predicting the behavior of linear time invariant system and for implementing the discrete time system on a computer. Okay. Now the thing is like in this case about linear time invariant theory. What is this actually? So this is popularly known as the LTI system or LTI system theory that comes from applied mathematics and has direct applications in NMR spectrology, seismology, circuit signal processing, control theory, and other technical areas. It actually investigates the response of a linear and time invariant system to an arbitrary input signal. The trajectory of these systems are measured and tracked as they move through time. For an example, the acoustic waveform. For applications like image processing and field theory, the LTI systems also have trajectories and spatial dimensions. A very good example of LTI systems are electrical circuits that can be made up of resistors and capacitors and inductors as well. Okay. So now this LTI system, that is linear time invariant circuits, these are actually made up of two terms, linear and the time invariant. Let us see what does it mean actually. So the thing is, let me describe it to you. First point is something about linearity. Okay, so let me write the details for this. It's about linearity. Okay. Now about the linearity, if we talk about it, the relationship between input and output of the system is a linear map. If, for example, let's say we have some inputs, that means like x1 based on time, so providing the output like y1 t. Similarly, we have x2t, which is providing the output to you as y2t. Okay. Now the linear for linearity setup, this if we multiply this input by some scalar and add them, the same kind of effect should be visible in the output as well. Okay. So it simply means like the relationship will be something like a1, which is like your scalar. Okay. Then we have x1 of t plus a2. Okay. We have x2 of t. This should provide the output like a1 times of y12 plus a2 times of a2 times of y2 t. Okay, this is the fundamental condition for your linearity. Fine. So let me highlight it. Now the next condition, next case over here is your time invariant. Time time invariant. Like whether we apply an input to the system now or t seconds from now, right? The output will be identical except for the time delay of t seconds. For an example, it is something like, let's say, we apply input by the time it's like x. This is my input, and I apply it, let's say, after t seconds. Okay, this is my time, and this is the time period of delay. It's like this actually. The output will be, again, the output will be same here, but that will be delayed by t seconds. Okay, so this is the case for the time invariant. Got it? So the combination of these linearity concept and the time invariant concept makes a system linear time invariant. Okay. Now the thing is like the fundamental result in LTI system theory is that any LTI system can be characterized entirely by a single function called as system impulse response. In our previous lectures, you might have seen about the impulse signals and all that. So if you have not seen, please refer to our previous lectures also. Now, the output of the system is simply the convolution of the input to the system with the system impulse response. That simply means like if you have a system, okay, that system has some impulse response, that is a response to the impulse signal, and if you apply your some input on that, the output will be the convolution of the applied input signal and the system impulse response. It is something like this way. Let me drag it down. Let's say you have some system. Okay. And let's for an example, we have impulse response which is given by xt. Okay. We have input signal, something like this. This is xt. Okay. And you will be getting some output from here. Right? This will be, let's say, yt. Fine. So actually what happens, this yt should equal to the convolution of this system impulse response and the applied input signal xt, and the convolution over here is represented by this asterisk signal, and this is like over here. Okay, let me help you out on this. This particular symbol over here, this is called as a symbol of convolution. Okay, this is the symbol of convolution, and this is nothing but actually a kind of integral ranging from minus infinity to plus infinity, and like product of the entire system divided by tau, that I will explain you. Something like let me write it for you. Yeah, this is like this integral. Okay, this is ranging from minus infinity to plus infinity. Okay, and it is like x of tau and h of, and that multiplied by h of t minus tau. H you know very well, this is the system impulse response actually. Okay, tau d tau. Fine. This is something called as your convolution. Convolution server. Okay. So now the thing is like, in case of this time invariant environment, we have a lot of other features as well. Let me go back to my presentation. If your signal, the system, is characterized in your time domain, if the signal is represented in the time domain itself, then we will be taking convolution to find out the response of a particular signal over the system. In that case, this method of analysis is often called as time domain point of view. And the same result is true for the discrete time linear shift invariant system as well, in which the signals are discrete time samples and convolution is defined on sequences. As a similar goal, like any LTI system can be characterized in the frequency domain as well by the system transfer function, which is the Laplace transformation of the system impulse response, or Z transforms in case of discrete time system. Okay, so now let me explain about a formula which is related to your setup actually, or how you can implement this formula over here. So here also, let's say these are the two functions, out of which one function is your the first function is the impulse response, and the second function, let's say this is the input signal, or vice versa, whatever it is. Now what does it mean if I say about ft minus tau? What does this particular point mean? It simply means like we are rotating one function of these out of these about the y-axis. We are taking a mirror image, and then the next important point is t minus tau. That's the important part of application is t minus tau. This is your shifting the same function by t. That means you can shift it to your some related point actually. Then third one is like we are taking the product of these two functions. That means you are multiplying the flipped function and the time shifted function. Flipping means like you are taking the mirror image about the y-axis. Okay. Now The question arises over here that which function to be flipped, whether the system impulse response to be flipped or we need to flip the input signal. So guys, the point is you can flip any of the signals, whatever signal is easy for you, whatever setup is easy for you, you can flip that. Okay. After that, the rest of the scenario is something like about this integral part. This integration is actually showing you the area of the part which is under the product. Okay, this one calculating the area under the product, and then you can assign this value of f1 cross f2 or f1 convolution to f2. So let me do one thing. Let me show you one working example over here. Alright, so that you can have a better idea like how this entire system works over here. Fine. So let's take one sample. Let's take one example over here, and let me explain this to you how it actually works on this. Right. Let me delete all this that you can have a better view. So this is the case. So let's say first of all I have one input signal. Let's see. Might one little bit got right. Okay. So this is the coordinate system, which is like where this is your time axis, and this is your function axis. Okay, and then we have this is our input signal. Okay, this input signal, it is 2, here it is 2. Okay, this is the input signal, and the system impulse response that we are going to get over here is something like this. Right? This is the coordinate system. Again, we have t, and this time I have an impulse response, let's say, by system gt. Fine. This impulse response is something like this. It has an altitude of, let's say, 3, and ranging from 2 to -2. Okay. Now we need to find out this, convolution, or like let's say if input, if this input is applied to this particular system, what could be the result? Right. This is my requirement. I would like to find out what could be the result. Right. So you can understand this kind of scenario in various aspects of your engineering, as well as whenever you go for your further studies or further career or something like. If you go to some kind of engineering setup, wherein you can understand, like if you have a system and you want to apply some kind of signals on that, what are the expected output, right? If you go to some kind of humanities like your economics and all, you should be able to understand, like if this is a situation that a system has this kind of response to the impulse input, and we are going to apply this kind of signals or something like, then what should be the expected outcome. So these are the details where you can apply this kind of setup actually, that we will discuss in some other lectures as well. But however, let me start from the first topic. So first of all, what we need to do is like we need to flip any one of these two signals. So you can see here that comparatively this signal here, like GT function, is much more easy to flip because it's not at all going to change actually, right? It is easy for us, so we don't have to do some extra calculations and so on. Right? We can just flip it, and we can we can make it slided over the axis so that we can have some overlapping. So the overlapping is something like, let's say let's say if you flip the function, first of all, if you flip the GT, it will not change actually, right? It will remain same actually like this. But the thing is like in this case, if I talk about the overlapping, how it actually looks like, let me show you. Let's say this is the case, and let's say you make some flipping and overlapping. This will be done something like this. See, okay, it's something like that. So here this will be 2, this will be 2, this will be 3. Okay, then here we will have it will be like 2 plus 3. Okay, and will be minus 2 plus 3. Fine. So these are the coordinate points actually. We have this and this. Now the thing is like, see, and this time the area that I was talking about is the area of overlap, where we have this kind of area which is overlap over here like this. Okay, so if you have a closer look of this kind of setup actually, so what happens, we come up with 5 different cases. Let me discuss all these cases one by one. First of all, we have kind of case number 1. Okay, case 1. Under this case 1, we have a situation where t is less than minus 2. T is less than minus 2. Right? In that case, what will happen? Okay. In that case, first of all, this flip function, t is less than minus 2, it means like, let's take an example, t is equal to minus 3, right? So what will be the first point? First point will be minus 2, minus 1, minus 2, minus 3, it will be minus 5, right? So the first point will fall around minus 5. And the second point, just 2 minus 3, that is minus 1. It will be like minus 1. And this will be your function gt. And this will be your function ft. Right? You can see here that there is no overlap between gt and ft. Right? If there is no overlap, then the area enclosed will be 0. Clear? So we don't have to, if you multiply it, the result is nothing but just the 0. Clear? Now, next thing is something like case number 2. under this case, we have something like, you can say, minus 2 is less than equal to t or less than 0. Under this, we have minus 2 is less than or equal to t, and t is less than 0. Okay? In that case, let me take one example. Let me show the coordinate system first of all, like this. Okay. Okay, so let's mark it. Let's say t is equal to minus 1, for an example. Fine. In that case, what will happen? In that case, here it will be like t is equal to minus 1. So what happens? Minus first point will fall in minus 2, minus 1, that is minus 3. Okay. So it will fall at around minus 3. Fine. And about the second point, 2 minus 1, that is 1. This is 1. Okay. We have something like this. Okay. This will be our system, that is your GT. And this time, our function ft will be something like this. 2, 2. Right. You can observe that we have a partial overlap over here. You can see a partial overlap over here. It means this is the time we are supposed to find out the area. Right? Now, the thing is like, I've just, given this value like minus 3 or 1 or something like that. But actually what it may be anything. I've just taken one example for you, right? So this is nothing but, actually this is equal to 2 plus t, and here this is minus 2 plus t. I've just given it for an example that's how actually you can plot a graph. So this is like here, okay, minus 2 plus t and 2 plus t. These are your actual points. So what we are supposed to do, now we have to calculate this area which is highlighted with green color. Alright, here this is 0. Fine. The function, if you have a closer look of this function, this ft, this is somewhat equal to minus t plus 2. Right, if you can have a closer look on the function, if you want to understand how we can, what are the different functions, we will have a different class for the same, minus t plus 2. Okay, something like this. Right, this is the function. Now, here we can proceed it. So, in order to calculate this area, this is the area enclosed over here, we can integrate this system, integrate it, create an integral. Integral should run from 0 to 2 plus t, okay. Then this one, that will be equal to 3 actually, you know very well. Right, this will be a constant during this range, 3 into, what is the function? This particular function is minus tau plus t, or t plus 2. So minus t plus 2, and we have already replaced it, minus tau plus t, tau plus 2, minus tau plus 2 theta. Okay, then What is the result of this? Again, this will be like 3 into minus tau square by 2 plus, yeah, 2 times of tau. Okay. And the range over here is from 0 to 2 plus tau, right? 0 to 2 plus tau. So what will be the outcome? The result will be something like, we have to replace this tau with 2 plus tau. So it will be something like, first of all, minus 3 into 2 plus tau square 2 plus tau square 1, 2. Okay, plus, what is that? This is 6 into 2 plus tau. 6 into 2 plus tau. Okay, this will be equal to, well, if you take a sum of this, once you solve it, you will get it minus 3t square by 2 minus 3 into t square or tau square, you can say, by 2, 2 plus 6. This is your second case. Similarly, let's move towards the third case. That is case number 3. Okay. Case number 3. Okay. Under this case, the condition is, let's say, 0 is less than or equal to t, and this t is less than or like that 2. Okay, this is the case. So now let's see what kind of graph it will be visible to us. Here we can see that we can achieve a kind of, let's say we can have a graph of, now I'm not putting any values like this to avoid any kind of further confusion. Okay, and we can see here that this time we can achieve a kind of complete overlap. Under the complete overlap, it is something like, let's say, if like 2 plus t, okay, and it will be like minus 2 plus t. Fine. So here we have a kind of complete overlap. So we can put it something like, alright, this is my complete overlap setup. So now we have to find out the area under this product, right? So now the total overlap area is lying between 0 to 2, right? So we have to perform the integration with this particular area. Now, how you can do that? Simply go ahead, like you can go for integration. Integral is to be done from 0 to 2. Okay? Then you have ft and gt. So the same setup, that is 3 times of minus tau plus 2 minus tau plus 2 d tau. Okay? Now, by this you will get your final product to be equal to 6. You can just integrate it just like above actually and put the values 2 and 0 over there respectively, and you will get the result as 6 between this particular range. Okay, I hope it's clear up to this point. Let me do one thing. Let me highlight this area so that at last we can put up finally. So for the case number 1, the final result is this. Okay. For case number 2, the final result is this one. Okay. For case number 3, the final result is this one. Okay. And then we have case number 4. Case number 4, under this case, we can extend our limit, and we can extend it to something like, let's say, 2 is less than or equal to t, and this t is less than 4. Right? These are the hard-coded values. Let me plot the graph for the same. Okay. So let's see what happens. This is 2. This is 2. Okay. Fine. So this time as well, if I plot a graph, it should something like this way. Okay. We can have 2 plus tau and minus 2 plus tau as these extreme values. Okay. Now again, we can see here that we have a kind of uh, the partial overlap, and we need to calculate this set of area. Again, the same way whatever we have done in this case, right? In the case of case number 2, the same setup we have to do. However, we have to change the limits actually, and the limits are from minus 2 plus tau, okay, to 2. Fine. And then the same set of functions, that is minus 3 minus tau plus 2, like this, 3 minus tau plus 2 d tau. Okay. Again, this overlap is there, and it will give you some kind of uh, like square function actually, right? Just like you have seen in step number of case number 2. Now about the case number 4. Case 4. Oh, sorry, this is case 5, right? Case 4 we have already seen. Case number 5. Case number 5 is something like t greater than or equal to 4. Okay, something like this way. 2, 2, okay. And if it is greater than 4, then obviously this time also there will not be any kind of, yeah, overlapping, where it is minus 3 plus 2 or minus 2 plus 3 actually. Let me overlap it. Minus 2 plus 2. This is the first point. And the second point is 2 plus 2. Okay. So this is how you can see that again the result will be 0 because there is no overlap. So the multiplication will be 0 and so the result will be 0 for case number 5. Right. Now by this we can simply conclude, like if we draw the final output of this two signal, which is for which we have done a convolution. Alright, to try to plot this graph, right, how it actually looks like. Let me use this one. So for the first case, that means less than minus 2, right, it was 0. So 0, like here, okay, up to minus 2. Fine. Now minus 2 to 0. Minus 2 to 0, it is showing you the negative square function, right? Negative square function over here. So it means like it should be something like, you can say your curve will be something like this way, right? And at 0, that is from case number 3, that is 0, it is up to 2 plus 2, from 0 to plus 2, it will be positive constant 6, right? So it will be something like this will be 6, okay, this will be 2. Now, if 2 is greater than, t is greater than 2 and less than 4, it is showing you this again. It is showing you the kind of square function, but this time it is positive, so it will be something this way, like this. And at 4, it will be 0. So it will proceed towards your line. So this is what the response of the convolution or result of the convolution, or in other words, you can say how this system, given system, will respond to a signal like this. Okay, so this is how we can solve some basic problems on signals and systems. This is how we can work on that. So I hope you like this video, and if you have any query, any question, please feel free to write your comment on the comment box. And please share and like and subscribe this video so that it will reach a better audience, and we can proceed accordingly. Have a nice time ahead and take a very good care of yourself. Okay, bye bye.